Hello everyone, hope you're doing well. So in this video, we're going to be going into the next part of the endocrine system and going over a little bit about homeostasis and how the endocrine system plays a role in it. But so we have to actually jump back to chapter 1 down here where we talked about where we have to define homeostasis because I don't think we talked about it then, and the seesaw of life and the balance we're constantly in. So we're going to talk about positive and negative feedback and what that means. And then we're going to look specifically at the role of the endocrine system in homeostasis and look at some examples of homeostasis within the endocrine system. So homeostasis, just to define it, is keeping your body stable. So we always describe it as a seesaw. If the seesaw goes off, you have an effect to bring it back. So you're constantly being regulated. So if your blood pressure goes up, you have receptors that monitor that blood pressure change and then you bring it back to normal. You walk outside, you start sweating because it's hot. You cool down, you shut off that response. So there are two different kinds of homeostasis. Most homeostasis in our body is what's called negative feedback, but there are some examples of positive feedback as well. Again, if you want to read about this, this is from chapter 1.5 in the OpenStax book. So here for negative feedback, you have a stimulus. So the stimulus is that temperature increase outside. Says your skin is getting hot. So that sensor senses that. Your control center, meaning your brain, says, okay, we need to now cool our body down before it gets hot. Then you send a response out to the effector, which happens to be the sweat glands. You sweat, and then that shuts off the stimulus and you cool back down. So the end product shuts down the first response that happens. And that's the key part to a negative feedback. So here is the example we just talked about. Sweat glands are activated, the body temperature drops back down, everything shuts back off. So it's all one negative feedback. So good examples in your body, your insulin, your blood glucose levels increase, you release insulin from the pancreas, glucose levels drop back down, and that does a negative feedback and shuts off the release of insulin. Now, to compare that with positive feedback, here it's showing an example of childbirth. So childbirth is a great example of positive feedback for the release of a hormone called oxytocin. So oxytocin is what's enhancing uterine contractions and pushes the baby towards the cervix. When that occurs, it causes the initial release of oxytocin causes more oxytocin to be released, then more and more and more. So it keeps increasing the amount of oxytocin release as the contractions increase until the baby is born. So oxytocin has a positive feedback where it increases the amount released the next time. Another example of positive feedback is platelet plug formation in blood clotting. So if you get a rupture in your blood vessel, platelets adhere to the collagen that's sticking out there and begin releasing chemical that encourages more platelets, and they release more chemical. So that enhances this platelet plug formation and tries to stop blood loss. And then if that doesn't work, you have a fibrin clot that comes in and seals off the area too. Now, looking at regulation of hormone secretion, we're just pretty much looking at a few different examples. So all hormones are regulated for how they secrete, and it all depends on a stimulus. So we just talked about that up here by going back. So some stimulus changes in the body. Calcium levels are wrong. Glucose levels are wrong. Blood pressure is high. Blood pressure is low. Like you can go on countless examples here. And so that stimulus, and you have a sensor that responds to that particular stimulus. And that's pretty much in essence how the endocrine system works. It's a constant homeostasis feedback working via your parasympathetic, mostly your rest and digest system. But your sympathetic system does have some endocrine activity, such as norepinephrine, epinephrine release from the adrenal gland. But here, this example right here is talking about CRH release, or corticotropin releasing hormone, which in essence ends up targeting the adrenal cortex, a gland on top of the kidney, to release your glucocorticoids. Glucocorticoids end up causing glucose levels to increase in the blood, allowing more glucose to be available for more energy use. So here, what happens? There's a sensor. The sensor says glucocorticoid levels are low, and the hypothalamus says, hey, it's low. We need to release more. Now, this particularly happens when you first wake up in the morning. And then you release that hormone. So up here in the hypothalamus and pituitary gland, they're connected and they're informing each other. You see these neurons coming down, causing the release of cells in here to release corticotropic releasing hormone, CRH. That CRH then travels to the adrenal cortex to cause the release of glucocorticoids. So your corticosteroids is another example. So glucocorticoids then go back into the blood. The levels increase to where they should be. That's a negative feedback. Then that shuts off more CRH release and the glucocorticoids do their job. So it's all homeostasis. If there's an imbalance, you respond accordingly. Another example here that we talk about a lot is insulin versus glucagon. So if blood glucose levels are low, so here blood glucose levels decrease. So you want your normal to be about 70 to 130 milligrams per deciliter. Well, what happens, well, no, I'm looking at this arrow wrong. But so if blood glucose levels are low, what happens is that glucagon is released into the blood from the pancreas. They're released from alpha islet cells. That glucagon causes the liver to release glucose. It breaks down glycogen or assists in the breakdown of glycogen to cause glucose to be released into the blood. So that causes blood levels of glucose to increase and we come back to normal. Whereas if blood glucose levels are high, say you just ate a sandwich, so that's the stimulus right here. Beta islet cells in the pancreas then release insulin. Insulin levels increase. That causes your cells to take up glucose, which removes them from the blood. The cells then can convert that glucose to ATP or store it themselves, or it sends it to the liver to be stored as well. That causes blood glucose levels to decrease and everything is back to normal. So not only do C-cells go one way, so you have insulin for this direction, you have glucagon for that direction. So there's another example. Another example here is blood pressure regulation and electrolyte balance. So your kidneys do a lot here in terms of blood pressure regulation. So here is the homeostasis. This is where you want to be. Normal ECF fluid volume, so extracellular fluid volume. So everything is fine. But let's say you lose volume in your blood or you have sodium loss in your blood. And that means you have decreased blood volume and blood pressure, and that's not good. If you don't have the proper blood volume, blood pressure, you could pass out. So you stand up too fast and the world gets black. That's because blood pressure has dropped going to your brain. So your kidneys release something called renin, which leads to angiotensin 2 activation and then can lead to aldosterone release and increase ADH or antidiuretic hormone. Now I know you don't need to know what these are yet. We haven't really talked about them yet, but all of these cause increased sodium retention and decrease water loss. Or so here ADH, increase water intake as well. So antidiuretic hormone causes you to reabsorb more water. Aldosterone causes you to reabsorb more sodium. So based on osmosis, if you have more sodium in your blood, more water is going to follow. So aldosterone and ADH kind of work together in that regard. And then your blood volume comes back up and homeostasis is restored. Whereas now let's imagine you have too much fluid in your blood. In your heart, you actually release a hormone called atrial natriuretic peptide. So here, increase NP, natriuretic peptide. So your atria stretch, and your atria sense that stretch in your heart. And they're like, we don't like that. We don't like that high pressure coming into our heart. So this natriuretic peptide causes decreased aldosterone, decreased ADH. So it decreases thirst, water intake, and does the opposite of everything down here, and eventually restores homeostasis and gets everything back to normal. Now, of course, if you have hypertension and chronic high blood pressure, this system is not as efficient. And so you can, if the seesaw's here, you've just moved the seesaw there, and it's not going to respond as efficiently anymore. So that was just a couple examples of this homeostasis feedback mechanism, but just know that almost all these hormones have a similar chart in how they work here. I just wanted to give a couple examples I could find, go over homeostasis, since we didn't talk about it in enough details back in chapter 1, and talk about the rules in the endocrine system here. That's all I have for this video, and see you in the next one where we go over all of the hormones, and not all, but most of the important hormones found in the body. All right. Bye bye.